Yes, am I audible, Harsha?
Yes, ma'am.
All right. So yes, in the last class we had started with elastic bodies and elasticity. What all things we have discussed? Elasticity was the first topic that we discussed. What is meant by elasticity? It's basically the tendency of the body to regain its original shape back. When you remove the deforming force, then the body tends to regain its original shape, size back. Already, original configuration. Original configuration means length, volume, or the shape. These are the configuration which we'll focus on. Then deforming force means what? Deforming force is the force that tends to produce distortion in the body, some sort of deformation in the body. And when you remove this deforming force, the body either becomes plastic, that is, remains in its state exactly after, or it can happen that it becomes exactly the way it was before the application of deforming. And yes, one more thing, plastic bodies are what? Plastic bodies are just exactly opposite to that of elastic bodies. Plastic bodies do not have the tendency to regain their original shape back. Plastic bodies, they cannot regain their original shape back. So this property only resides by elastic bodies. So the types of deformations also we discussed. There were three types of deformations: change in length, change in volume, and change in shape. This much we all have studied. Coming to stress, I told you two topics we'll study: stress and strain, which comes because of change in the parameters, these change in deformity. Now we all have studied, you all have studied pressure. Pressure, you people know. What is the formula of pressure?
Force by area.
Yes, Harsha, what's the formula of pressure?
Force by area, ma'am.
Force by area. Very good. Now listen, stress is also a type of pressure only that is being exerted. See, suppose this is the wire that has been taken and a deforming force is being applied downwards. All right. There must be some area of this cross section when we are talking about a wire. Some area must be there. So in 1 meter square, in just this 1 meter square, how much deforming force is being applied? In just 1 meter square, how much deforming force is being applied? That is what is meant by stress. So stress is what? Stress is the deforming force by the area. It's the deforming force per unit area. So again, the way Harsha, you were mentioning the formula for pressure, stress is also force per unit area. So stress is deforming force by area. All right, this is what is the formula of stress. So in 1 meter square unit, in 1 meter square of area, 1 meter square of cross section, whatever will be the deforming force that is applied, we term it as stress. So deforming force per unit area is known as stress. So form definition is the internal restoring force acting per unit area of the deformed body. Why deformed body? See, because deforming force is being applied. That's why only deformed body. This force, no, this force is specifically the deforming force. That's why we are saying of the deformed body. So it's a scalar quantity. The way pressure is a scalar quantity, this is also a scalar quantity. You do not have any direction for stress. It's just that wherever force will be occurring, wherever area will be there. For the particular area, whatever force will be occurring. Now, SI unit. Yes, Martin, what should be the SI unit? What is the SI unit of pressure? Martin, you tell. SI unit of pressure.
Pascal.
Yes, very good, pascals. So basically, SI unit of force is what? Newton. SI unit of area is meter square. So when we write 1 Newton by meter square, either you can completely write this as Newton per meter square also, or you can use the unit pascals, which Martin has rightly mentioned, pascals. Because the ultimately it's force per unit area, and 1 Newton per meter square is also called as pascals. That's coming to dimensional formula. Dimensional formula of force. Force is mass into acceleration. Acceleration is L t to the power minus 2. Area is L square. Length will be cancelled. So this becomes M L to the power minus 1 t to the power minus 2. So this is the dimension. So this can be asked here also, and this can be asked in your unit 1.
Ma'am, is it a reaction force to the deforming force?
Sorry, what?
Ma'am, is it like a reaction force to the deforming force?
No, it's not a reaction force. The stress is not a reaction force. Stress is the pressure that is being created because of deforming force. The pressure that the deforming force is creating to pull the object to cause the deformity. That pressure is called stress specifically. But pressure we have, this is a type of pressure only. Dimensional formula is also same, unit is also same, formula is also same. It's just that stress we focus on firstly for solid objects. That's why we have a separate term. Secondly, this is important for deforming body. This, as I was mentioning, deforming bodies is necessary. Force per, if had it been only force per unit area, this would have been normal pressure. Right now, when restoring force comes, and this is specifically for solid objects, that's why we say this is stress. Otherwise, it's not a reaction force. Had it been a reaction force, there wouldn't have been any area. It's just that this is occurring on deformed bodies. Clear, Harsha?
Yes, ma'am.
Now, note it down, all of you. Now see, as we discussed in the last class, that there was not a single type of deformity which was existing, right? Not the only one single type of deformity was existing. So if there are multiple types of deformities, so it means multiple types of deforming forces will be acting on that area, right? So stress is also not a single type. You do not have just one term as stress. You have normal stress, which also has components tensile and compressive. You have tangential stress, you have volumetric stress. So stresses are also present depending upon the types of deformations caused. See, first one, let me discuss types of stress. Normal stress. Normal stress is a term that is used because the force is applied is perpendicular. This I'll tell you. But remember, normal stress or longitudinal stress, both are the similar type, same type of stress. It's just that two different names are present. We also call longitudinal stress as normal stress. The common term that will be used will be longitudinal stress. In reference books, in your NCRTs, you will find longitudinal stress much more available. But remember, normal stress is also a term that we use for the longitudinal stress. Now, what is meant by it? Suppose this is the edge of the wire. I've drawn it broadly also. This is the force that is acting. Now, this force is perpendicular, making an angle of 90 degrees. All right. When we are talking about the force that is occurring, either it's upwards or downwards. Or if you take a different surface, for example, suppose on a table here, some deforming force is acting. So this is perpendicular to it. So when the deforming force is perpendicular, that is the deforming force is applied normally to the surface of the body or the area of cross section in case of circular objects. Then we call the stress as the normal stress. All right. So formula of longitudinal stress will be the perpendicular force which is being applied per unit area. Just remember that this has to be 90-degree. Angle between the force and the surface, this has to be 90. That then only you will get the longitudinal stress. Now this is also of two types. Tensile stress you have, and then you have compressive stress. Now see, suppose here the force is applied downwards, it is pulling the body downwards. Fine. So what will happen? Ultimately, there is an increase in the length. There is an increase in the length, slight increment in the length. So remember I told you tensile, compression. Yesterday, I think we have discussed this in the type of deformations. Whenever there is a change in length, I told you, no, when the length increases, we call it as tension. I also showed you figures. See, when we are talking about the types of solid deformations, when we are saying change in length, when the force was applied and it increased the length to this height, we called it as tension. And whenever the force, this was applied in such a manner that it compressed the body, so this was called as compression. So that's why based upon these deformities, we have the stress also. So if there is an increase in the length of the body, then we say this is what? If there is a increase in length of the body, then in the direction of applied force, the stress setup is called tensile stress. Fine, this is what is the definition of tensile stress. If there is an increase in the length of body in the direction of applied force, the stress setup is called tensile stress. On the other hand, you have compressive force if there is a decrease in the length of the body. In the direction of applied force, the stress setup is called compressive force. These are the two types. These are the subheadings of longitudinal. So till now we have just discussed one, where the component that is changing is the change in length. This is the component that is changing. Either it's increasing or it's decreasing. But there is a change only in the length. And the one more condition which is essential is theta is 90. Note it down. Now see class, the second one is tangential stress. Tangential stress, basically, this brings out the change in shape. Brings out the change in shape. So I gave you an example also yesterday that you will be applying a force. So the best example is the textbook, because they have the ability to have their base at the original position and shift their upward surface. So this is theta. Now the difference here is that the force that is applied is parallel, exactly opposite. That was perpendicular in volumic, in longitudinal. Here the force that is applied is parallel. Force will be parallel. And see, when I'm talking about the area means this area, the upward area, this area, the top surface area. So again, when we are talking about tangential stress, this is also force, that is parallel force which is being applied per unit area. SI unit will also be the same, Newton per meter. So if the deforming force is applied parallel to the surface of the body, then the applied force per unit area is called the normals, not normal stress. This is tangential stress. This is tangential stress. Last one, volumetric stress. See what is meant by volumetric stress. Again, I told you one of the parameters that yesterday we discussed was change in volume. So volumetric stress will obviously bring out the change in volume. This is helpful in calculation of change in volume, right? Now, suppose this is a sphere. And from all directions, force is being applied. This force will also be perpendicular. Mostly these forces are also perpendicular. But the reason is the difference between longitudinal and volumic will be that they'll bring the change in volume. If they'll bring the change in length, then that is not volumic, that is longitudinal or normal. So these forces will also be 90-degree, because on the surface of conductors or spheres, whenever the forces are applied, it becomes parallel. So ultimately, it will result in what? This will result in the shrinkage of the surface. So if it was V volume initially, some V dash new volume will be existing. But apart from this, there must be some area of the sphere. So again, your volumetric stress is equal to the force. Now this is also perpendicular force applied by area. So if the deforming force is applied perpendicularly on a body which changes its volume, then that deforming force produced per unit area is called volumetric stress. These are all the types of stresses that we have in nature. Write down this.
Ma'am, what is stress denoted by?
There is no symbol for stress. You have to write the complete term stress. No symbol for stress. No symbol for stress. No symbol for strain.
Okay, ma'am.
Yes, so the second quantity that comes into action whenever there is a change produced, we get strain. Now, strain means what? Whichever dimension is changing by the original dimension. See, strain is basically whatever change is occurring, that is meant by strain, the amount of change that is occurring. So how do you calculate the amount of change? So change in dimension by the original dimension. Dimension, what all dimensions are possible? Again, length, area, volume. All the three types of dimensions are possible. So the change in size or shape of body due to deforming force is called strain. So if you have the same dimension above and same dimension below, like length, change in length, original length, length will be cancelled. Change in area, original area, change in volume, original volume. So what should be the unit of strain? What should be the unit of strain?
It's unitless.
It's unitless. Very good. This is unitless. No SI unit exists. It's unitless plus its dimensions. This is not important from your this lesson's perspective, but you have units and dimensions, the very first lesson. So for that, you should keep these things in mind. Unitless and dimensionless. So if you are asked to write a quantity which is unitless as well as dimensionless, it will be strain. If dimensionless but having units, you will mention angle. Angle is dimensionless quantity, but SI unit is there, radian, and stay radian for 3D. All these things we have done initially in our initial classes. Now again, if the dimension that is changing is not of single type, so the amount of change will also be not of single type. We have longitudinal strain. See, longitudinal strain means, suppose this is a wire of length L. It has increased its length to L dash. Fine. So there is a change in the length that we can notice. Can you see delta L is the change in the length? And L is the original length. L was the original length. So when we are talking about the longitudinal strain, this is the change in dimension. So what is the change in dimension? L dash minus L, right? L dash minus L will give you delta L divided by what was the original dimension with which we started. All right, this delta L is the change in the length, which is L dash minus L, and this is, so this is the formula of the longitudinal strain. So why longitudinal strain? When the change in length is there, again the same thing, longitudinal stress, longitudinal strain. Change in length gets produces longitudinal stress and longitudinal strain. So when the deforming force produces change in length alone, only length is changing, strain produced is called longitudinal strain. Strain produced means the change that has occurred, that is called as strain. Stress is the pressure that is being exerted, while strain is the deformation. See, stress is the pressure that is being exerted because of deforming force, and strain is the change that is being resulted because of the deforming force. Write this down. Now see, in volumic strain, the change that will be produced will be the change in the volume. So when the deforming force produces change in volume, like I told you, forces are being exerted from all the directions. So this results into what? This results into compression, and forces will be 90-degree. Suppose this has reduced to some V dash. Initially the volume was V. So can you see there is this change in the volume that has occurred, delta V. So V is what? V is the original volume. V dash is the new volume. And delta V is the change in volume. So volumetric strain will be delta V by V. Original, a change in the quantity, change in dimension, so change in volume by original volume. Again, you can check even meter cube by meter cube will cancel each other. So no units are there, delta V by. And what is delta V? Delta V is V minus V dash. All right, the change in the means the new volume minus the initial one, or initial volume minus the new volume, depending upon which one is greater. If suppose the deforming force have occurred within inside, that will lead to expansion. But here we are talking about compression. Fine. Note down this. Now, see, when we are talking, this is shearing strain is the last one. Third one. All right. So shearing strain is when the deforming force produces change in the shape of body. So see, when the deforming force will be acting over here, this is the length. Here is the change in length that is being produced because of the shift of the surface, right? And this is theta. So A, B, C, I have named this triangle as ABC. This is the shift that has occurred. Now, look here. In this triangle ABC, if I say tan theta will be perpendicular, that is BC, upon base, that is AB. So this becomes BC divided by AB. So tan theta is delta L by L. See, BC is what? BC is delta L. If you look at this triangle, this is theta, this is C, this is B, this is A point. This is L, this is delta L. So tan theta is delta L by L. Now see, for very small angles, I think I've mentioned earlier also that tan theta or sin theta, they are almost equal to theta. So theta is the shearing strain, that is change in length by original length. This is the shearing strain. Because shape is giving you one of the parameters, that is length is changing. So this is actually equal, or the formula is exactly similar to that of longitudinal one. So this sometimes comes to derive shearing strain. The rest of it will not come in derivation because no such derivation is there. But shearing strain in two marker questions can come. Write this down as well. So when the deforming force produces change in shape of the body, the strain produced is called shearing strain.